Hello guys, this is CodeNCode and this is a video editorial for this problem weekend common divisor taken from Codeforces, rated 1600. This number is also from number theory category. So the problem is during research dash 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 dash. So basically we are given n pairs of numbers, right? And we have to calculate their weekend common divisor, which is any number which is greater than 1 and divides at least one of the numbers from each pair. So for this number, weekend common divisor are 2, 3, 5 and 6. You can print any. For example, take 2. 2 divides 12, okay, but doesn't divide 15, so it doesn't matter, because from each pair that number must divide at least 1. So it divides 12, divides 18, divides 10 and 24 both, but it doesn't matter since it divides each at least one number from each pair. So this is weekend common divisor. The rest so is true for the rest. So we have to find and report and print one weekend common divisor, otherwise I think we have to print -1. So if we take the first example, 17, 18, 15, 24, 12, 15, the answer is 6, because 6 divides 18 from the first pair, 24 from the second pair and 12 from the third pair. So it divides at least one number from each pair, so that is why 6 is weekend common divisor. And for these two pairs, 10, 16, 17, there is no number that divides at least one number from each pair. See, the problem is 7 and 17 both are a prime numbers, so these number must be multiple of either 7 or 17, but none of them are. So you see, the only number that can divide 7 is 7 itself, greater than 1, because we have to print the number that is greater than 1. So for this pair, 7 would only 7 would divide this number, but none of the number are divisible by 7. For this number, only 17 would divide it, and none of the numbers are divisible by 17 in the first pair. So the answer is -1 in this case. This is the third example, and answer is 5, because you can see this number, this number, this number, this, everyone, at least one number from each pair is divisible by 5. So first thing you should do is pause the video and think for yourself how you can solve this problem efficiently for the constraints. Each element in the pair can be as large as 10 to the power 9, 2 into 10 to the power 9, and there are no more than 1.5 into 10 to the power 5 numbers. So just think how you can do this. The expected complexity should be n log n or n log n square. Both would do, I guess. So just think about this, how you can solve this problem, then continue. So the possible approach for this problem is, since we know that, okay, if the answer exists, then the number is divisor of either, we are only thinking about we must need a starting point, right? So the starting point for us can be the first pair, right? So since the weakest common divisor, W weakest common divisor, is a number that divides at least one of the pairs, right? So what we can do is create a list of all the divisors from first pair. That is this: 2, 3, 6, 9, 18 and 17 are the divisors of 18 and 17. Now since these you can consider as your, what we call it, candidates divisors. So since the weekend common divisor must divide at least one of the pairs, so it must be a divisor of either 17 or 18, right? So that is why I have taken a set of this set is actually union of divisors of 18 and divisor of 17, because this number, the weekend common divisor, is at least divisor from these two. So what you can do for the starting point, create a list of divisors of first pair. That would be your candidates, and for each number check whether this number is the weekend common divisor or not. If not, then continue, otherwise print that number. So we would go for 2. Let's start for 17 because 2, 3 and 6 are actually answers. So let's start from 17. So 17 divides it, okay, but 17 doesn't divide any of the number from these two, so 17 can't be weekend common divisor. So we would go for the next number, which is 18. 18 divides this, but 18 doesn't divide any of the number in the next pair, so 18 is not the answer again. Then 9 divides this, but 9 doesn't divide any of the number from the next pair. We go to 6 divides this, 6 divides this, and 6 divides this, so 6 is the answer. So this is one of the way to approach the problem. It's simple. All you have to do is create a list of the divisors of A and B from the first pair. After that, for each number in the list, check whether that number divides at least one number in the remaining n-1 pairs. If so, then that number you can print, otherwise we would continue. And if none of the number from the list divides the number, then we would print -1 because there is no weekend common divisor for this. So this is the starting approach of us, but we must analyze it whether this is sufficient to pass time limits or not. So the upper bound on number of divisors is cube root of n. The number can be as large as 2 into 10 power 9. If I assume only 10 power 9, then cube root of 10 power 9 is 1000. So for our divisor list can contain as large as 2000 numbers, 1000 from first, 1000 from second. So the divisor list can contain 2000 elements, and the number of pairs are 1.5 into 10 power 245, 1.5 into 10 power 5, and the divisor list would contain 2000 divisor. For each divisor, if we run a loop for the n number of pairs, then the overall complexity would overall number of operations roughly would be 1.5 into 10 power 8. Usually 10 power 8 operation are done in 1 second, so 1.5 into 10 power 8 number of operation would result into 1.5 seconds, which is the time limit. You may think that this would pass the time limit, but the problem is it would not. The reason is because in these 1.5 10 power 8 number of operation, we are doing the heavy operations, which are modulo operations, and finding the divisors requires division, again modulo operation. So modulo among all of the arithmetic operation, namely addition, subtraction, multiplication, division, modulo, multiplication and division are the most costly operations, and the best operations are bitwise operation because that can directly be performed on register. So if you try to approach the problem this way, you are surely going to get TLE. So how we can rectify this, or how we can enhance our solution? See, we are not going to change the initial approach. So what we are going to do, let me ask you a simple question. Do we really need 6, 9 and 18 in this list? Just think for a second and think why I didn't ask for 2, 3 and 17, why I'm only asking for 6, 9 and 18, why I'm only being racist to 6, 9 and 18. Just think for a second. The reason is these are composite numbers, while 2, 3 and 17s are prime numbers. And the claim is, if there is a CWD is a weekend common divisor, WCD. If there is a WCD of all the pairs, then and it's a composite number, then there must be a prime which is also a CWD or whatever that is, weekend common divisor. If you find a number like 6 which is composite number, then there is also a prime which is weekend common divisor. Now why 6 is weekend common divisor, which means 6 divides at least one number from each pair. Now 6 is made up of prime numbers 2 and 3. So if 6 divides at least one number in the one number in these n pairs, then 2 and 3 will also divide. So we don't have to actually keep the composite number. All we have to do is to keep the prime numbers, because if there exists a weekend common divisor which is composite, then there exists a prime number which is weekend common divisor, because if number x divide another number y, then all the divisor of x also divide y. So if there is a composite number, then there is a prime number. If so all we have to do is keep the list of prime. We don't need these composite numbers. So the question is how it is going to affect the size of this, because the overall complexity of course depends upon the size of this list. Now see, for a number there are no more than log n different primes, so the list size would be 2 times log n. So the overall complexity would be n log n, and hence we would be able to pass the time limits. So all we have to do is take the first pair and create a list of all the prime divisor of a and b, and then for each number in the list A, we would check whether ith number divides at least one pair, at least one number from each pair, from 2 to the nth pair. If it does, then we would print that number. Otherwise we would print -1 if none of the number is weekend common divisor. So let's jump into the editor and start coding. So first we need let's create a list. Let's call it A, or prime divisors. Okay, now add primes. What this function will do, long int, I'll explain in a moment. So we are given n. Since n can be pretty big, we also need to save. LLI is long int. I have defined I've used hash define to define LLI as long int. So I'm creating an array to store the pairs. A and B would store the A and B of each pair. So this is the array, this is the list, this would be the list of prime divisors. So what we have to do is int n, sin n. After that we also need, let's take A and B. Oh sorry, doesn't matter. So we will now read the n divisors. So now we have taken input of all the pairs. Now let's, what the function was, add primes. Add primes AR of 1, AR of 2, not AR of 2, BR of 1. So add primes would what add primes would do, for these two numbers it would add all of their prime divisors in this prime divisor list. So how you find prime divisors of a number, I have already explained in my number theory course series. So if you have no idea, just go and check out that lecture. So we run a loop from 2 to square root of I, or to square root of n. If n is divisible by I, which means I is the prime number, so what we are going to do, while n modulo I is equals to 0 and divide equal I. So what we are doing, we are removing all of the in prime representation of n, we are removing all prime I. So if n was 2 raised to power 2 into 3 raised to power 5, so of course n is divisible by 2, so we would remove all appearances of prime 2 from the number. So if it was 2 raised to power 3, so you would divide it by I, it would become 2 raised to power 2, then 2 raised to power 1, then 2 raised to power 0. So basically it would remove all the appearances of prime I. So the next number that divides is not any multiple of I, and hence the next number that divides is again a prime number. So after that, prime div, since I is the prime number that divides n, so we must add it into our list. I is a prime divisor. And finally, if n is greater than 1, which means n itself is a prime number, so now you might think that what if in the pair a and b are same, then prime divisor list would contain the same number two times, same prime divisors two times. So yeah, that is very true, but it doesn't it would not affect the overall complexity, so it doesn't matter. You can keep a set, but that again is going to increase the complexity by a factor of log n, because you need to insert an element, it takes log n time. So I'm not going to do that. So what we have done till now, we have taken the first number and second number and created a list prime div, which contains all the prime divisors of these two. So all we have to do is run a loop for each divisor d in prime div list. We would run a loop from 1. You don't need to run a loop from 1 because d already divides at least one number from first pair, because this is of course the prime div contains all the divisors or prime divisors of first pair, so it must divide first number. So you can start from second. If AR of I modulo d is not equals to 0 and AR of I modulo d is not equals to 0, which means neither first nor second number is divisible by this prime. So before going into the loop, we would initialize a flag true, indicating the answer exists. So if there is any pair in which none of the number is divisible by this divisor, then simply flag would be false, because this pair is not divisible by this prime divisor, and we would simply break. And finally, after running a loop from 2 to n, if flag is true, which indicates all of the divisors are divisible by this, so we would simply print d and return 0. Otherwise we would continue for the next number. If after running through all of the d's in the prime divisors, none of the number had divided, we would reach here, because otherwise the program would return from here. So we would reach here, which means there is no number that divides all of the pairs, so we would simply print -1. This should work. Let's simply name this test. Go for the test cases. Okay, I know I'm going to get an error, sorry. Hash define, sorry, hash just a second. Oh, this is going to take just 3 or 4 seconds. Yeah, so let's go for the first. The answer is 2, because 2 divides this, 2 divides this, 2 divides this. So the answer for the first test case is right. Let's go for the case where the answer is -1. This. So the answer is -1, so it is working at least for the given test cases. So let's submit this. and see if we get any error. I need to remove this line, I need to remove this line, I need to remove this line, and then we can common divisor. Yeah, let's just hope we don't get any error. Okay. Submission. Oh, come on. You all know you are faster than this. Go on. Usually Codeforces doesn't take this much time, and it is really fast at giving you TLE or wrong answers. It's like, just try again. I'm hating this. Oh, come on. Go on, go on. This is really pissing me off. This has never happened. Literally. This is testing one by one. I mean, come on. Most likely we are going to get an AC, so I think I should stop. Okay, so till it is just testing around, so let me give you something that is important. So in the slides I've mentioned that yeah, sorry, here I mentioned that the upper bound on the number of devices is root cube n. So where did I get to the conclusion of this? So for that you can simply Google and go to a link for Codeforces, where there is a whole discussion going on the number of devices. So upper bound on number of devices. So on Codeforces there is so here it is. There's a guy M Mahdi have asked what is the upper bound on number of devices of a number. So he himself has derived or have came to a conclusion that the upper bound is 2 into square root of n, and he's asking for a solution that he cannot find a tighter bound for this. So there are guys like Yaputons, I guess. It is n raised to power epsilon, where epsilon is greater than 0, and usually in the practices we take the upper bound to be n raised to power 1 by 3. There are 2 links, you can go there and read how we have reached to the conclusion of this, or how we have derived this formula. So this was I needed to tell you, because it is not like I can go and tell you, okay, this is the formula for upper bound or something like that, and I don't expect you guys to believe me, because you must find it out yourself that whatever I am speaking is actually true or not. It is very important, because there may be because I read from some of the sources, maybe those sources are not completely or perfectly true, so I may make mistakes, so feel free to correct me. I don't know what is happening to Codeforces right now, but I'm going to stop here. And if I get any wrong answer, of course, I'm going to report. Otherwise, this is the correct answer, because this is just pissing me off 92 till now. So I'm just going to stop it. So thank you guys for watching, and most likely I'm going to get an AC. I'll also, this time at least, I'll be giving the link of the submission of this this submission, so you guys can verify that whether this was a wrong answer, TLE or something like that, or AC. So thank you guys for watching. I'm going to stop here because that's enough. Thank you guys for watching, and till the next video drops, keep coding. Thank you.